Some materials, if you deform them, will not return themselves to their original shape. For example, wet clay can be squeezed or pushed into a new shape, and then if you let go, it keeps that new shape. But some materials, if you deform them, they do return to their original shape. For example, a sponge or a volleyball or a spring. In this PHYS simulation, we can see that if I put this cylinder on this spring, the force of gravity pulls down on the cylinder and it accelerates the cylinder downward. But as it does, that deforms the spring that is attached to the cylinder, which exerts a force. The spring exerts a force that starts out at 0 newtons, but increases in magnitude the more the spring stretches. That makes the weight stop accelerating downward. We can see that the force of the spring equals the force of gravity in magnitude, and the cylinder is now held stationary. When the relationship between the amount that an object has been distorted and the force it is exerting to restore itself back to its original shape is direct, this is known as Hooke's law. It is named after the same Robert Hooke who first discovered cells by looking at cork under a microscope. Note that in this picture on the right side there's a long coil spring that looks like the one in the PHYS, but at the top there's also a 2D spiral coil. This relationship, Hooke's law, takes many forms for many different shaped objects, and in this course we will care about it for one-dimensional springs stretching like the one in the PHYS. Let me give a couple of pointers about springs and other objects that follow Hooke's law. First, the phrase ideal spring means that the restoring force is proportional to the amount that the spring has been stretched or compressed. That means the more you stretch or compress a spring, the harder it exerts a force to try to get itself back to its original shape. Secondly, a spring has an original length prior to distorting it, some length that it has when the total force on it is 0. That is represented as x here in this image. And then delta x, or in class I'll often use delta L, that represents the amount it has been stretched from its original rest length. Please pay attention to the wording of each question so that you don't get tripped up thinking that the original length is the amount it was stretched or vice versa. And the third thing is, note that if I stretch a spring to the right, the restoring force points to the left. By definition, that's what we mean when we say it is a restoring force. It is exerting a force in the opposite of the direction to which it has already been distorted. Thus, Hooke's law has a negative sign built in. Don't let this throw you off when you're doing your equations. The negative sign, which we see right here, is telling you that whether you have compressed or stretched the spring, you created some delta L, and the springy object exerts a restoring force in the opposite direction. Again, by definition, and again, that's why it's called a restoring force. One more note, an ideal spring can be stretched or compressed, either one. Make sure you know which one's happening in the problem. Of course, in real life, or in a Physics 240 lab, not all springs can do that. Also in real life, or in a Physics 240 lab, a spring that obeys Hooke's law will only do so until it's damaged. It is possible to stretch a spring to the point that it no longer follows Hooke's law. There's a whole subset of engineering based on destructive testing of materials, but for this course, if an object follows Hooke's law, then it does so perfectly. I did a little experiment that I'd like to show you to determine the spring constant of this particular spring that I'm showing on the left. Keep in mind, each spring has its own value for a spring constant. In this experiment, I took a force sensor on the right, and I used the same software from the kinematics videos. This is the experimental setup. I have the spring attached to the stationary ring stand, and I pull on the spring with a varying amount of force, and then I graph the amount the spring stretches relative to how hard I pulled. I chose to have the force on the vertical axis and the distance on the horizontal axis for reasons that will be clear in a couple of slides. I'm pointing this out because the force is the amount I'm exerting. That is my independent variable, so the amount that the spring stretches would be dependent, but the amount that the spring stretches could be thought of as the independent variable, and the amount that the spring itself exerts a restoring force to try to get itself back to its original shape would therefore be dependent on how far it has been stretched. Either way, I chose these axes for a reason that will be really clear in a couple slides. So here's a quick video of the experiment. The force sensor is on the cart, so there will be a smooth motion, and I have the motion detector on the right, so it feeds the changing distances straight into the data table and makes our graph for us. Again, the purpose of the cart is just to make the data smooth. And this is my graph. You can see the relationship is linear. The linearity is Hooke's law. I should note the graph is linear down and to the right, not linear up and to the right, only because of the way I have the motion detector measuring. The more I stretched the spring, the closer I was to the detector. So this is really a graph of spring force versus how close I am to the motion detector. A graph of spring force versus the amount it's stretched would be linear and upward. The point, though, is that the slope of this graph is 8.313 newtons per meter, and that is the K value, the spring constant of that spring I was measuring. That is the proportionality constant of the spring. I said earlier there's a reason to study Hooke's law beyond simply stating that some objects are elastic and those objects sometimes follow Hooke's law. And what I was getting at is simple harmonic motion, which is going to help us to do a lot of things like model how atoms in a solid structure interact with one another.